today. We have with us two fantastic speakers, both Pauls. First of our speaker is Paul Barrett, who is an astronomer at the U.S. Naval Research Lab.
Sorry.
Paul,
No, I'm
sorry.
at George Washington University.
Oh, are you at George Washington now? Thank you. Sorry about that. Um, he was one of the earliest adopters of Python in astronomy and is now also a Julia developer and will tell us about JuliaAstro, which is an ecosystem of Julia packages in astronomy. Um, Paul, I will give you a warning at 15 minutes.
Okay.
Thank you.
You want me to begin?
Yeah, please.
Can you see that?
Yeah. Yeah. Yeah.
Yeah. Okay. So JuliaAstro is basically the Julia kind of counterpart to AstroPy. It's a Julia repository and community for astronomy. And so I'm going to basically give an overview of what we're doing. We're a little bit younger than AstroPy, but we are making slow and steady progress. So I want to start out with why Julia was created. And the short answer is we were greedy. This is one of the four creators. This is from Jeff Bezanson. He says we want a language that is open source with a liberal license. We want the speed of C with dynamism of Ruby. We want a language that's homo-iconic with true macros like Lisp, but with obvious familiar mathematical notation like MATLAB. We want something as usable for general programming as Python, as easy for statistics as R, as natural for string processing as Perl, as powerful linear algebra as MATLAB, as good as gluing programs together as the shell, something that is dirt simple to learn, yet keeps the most serious hackers happy. We want it interactive and we want it compiled. In essence, they're greedy. They want everything. And hopefully, I think they've pretty much achieved their goals. Julia is a really nice language, particularly for scientific computing. It's designed for high performance scientific computing. As one of the original developers of scientific Python 25 years ago, Julia is what I envisioned 25 to 30 years ago. So I've been very happy with it. So why is Julia different? And we'll take Python. For one thing is Julia is composable. And unless you actually work with Julia and develop software, you really don't appreciate this all that much. But unrelated types, okay, or classes if you're from Python, just work together seamlessly, okay? So for example, there is a package called measurements, which allow you to do, value error pairs. And then there's a separate package called unitful, which allows you to add units. These were developed independent of each other, but they work together, okay? So you can do calculations of arrays and you can provide both, values and errors for these, and you can provide units, and they work very quickly and efficiently. So that's what they mean by composable. It's much easier to combine different packages together into a whole. Julia is concise. It's 2 lines of code can provide the same functionality. My personal experience, I can do the same thing in Python in half the lines of code, sometimes a third or a fifth. And of course, I get the higher performance. Julia is highly performant. It's on the performance of C and Fortran. It's typically 10 times faster than Python because it compiles to machine code. All right. And with a few optimizations, you can make it very fast and sometimes faster than C or Fortran. And that's a huge benefit. It's productive language, and that's still the rule of thumb that the number of lines of code is directly proportional to product, or inversely proportional to productivity. So the fewer lines of code that you need to write, the more productive you are. And that's important, I think, in today's development world. It's easy to maintain. The one thing that doesn't get a lot of exposure in terms of the community is its package manager. It has an excellent package manager, and in an instance, the code just works. And part of the reason for that is when you download a package, you say, I'll add this package, add measurements.jl. It goes off to the general registry, finds that package, downloads it in all its dependencies, and then compiles all of those at once, okay? So that means there's no version control issues. Everything just works together. It may take 20 or 30 seconds, but then everything just works, okay? If you upgrade to a newer version, you download the more recent version, everything is recompiled and you're ready to go. So there's no issues of version control and trying to figure out, why does my code not work? Why can't I get it to run? It just works. And of course, the big benefit, it's free and open software. So you can just download it and use it and just run with it. So how do you use Julia? Well, you basically install the Julia binary. You just go off to the julialang.org website. You can download a binary directly, or the preferred way is to use the binary installer called JuliaUp. And that will allow you, whenever there's an update to Julia, either a minor or major update, you can just, it'll go off search and say, okay, there's a new update available, and it'll download it for you. You can start Julia, and then the next thing you do is you can go into the package manager mode and install packages. Or you can just say using package, and it says, do you want to install this package? And it will install it for you. And as I said before, it will download all its dependencies and compile those at the same time. And then you can go off and use the package. The other aspect in terms of Julia, it's not an object-oriented programming language. It's closer to Fortran or MATLAB. It's a functional type language. So there are no classes. But when you use the language, you would never really know that, okay? There's a lot of similarities there. And the other difference is that in terms of mathematics or arrays, Julia follows the mathematical convention of one indexing and column major, okay? It's not like Python, which is zero indexing and row major. So it does follow the mathematical protocol. But usually that's not an issue, all right, when writing code or even using code, because normally you're using the entire array instead of subarrays. So now I'm just going to cover, what Julia packages are out there. I just want to say that, we're still young, we're still developing software, and things are not complete. Part of the reason is we really lack resources. We've really struggled to get funding in the past several years. And so that really kind of crimps, or limits what we can do. But here are some packages. If we will start off with some fundamental packages. There's astrometry.jl. This is a package to do basically SOFA or ERFA type of calculations for astrometry, basically positioning in time. As a sub-package, there is a pure Julia implementation of the SOFA subroutines, all 357 or so of them out there. They all run at basically C speed. They've been tested, so they run really quickly. There's fitsfiles.jl, which is being developed, which is a pure Julia version for reading and writing FITS files. There's a package called ASDF.2.jl for the advanced science data format. We're working on that. We have sky coordinates. We have the world coordinate system, WCS.jl. And then Julia has a package called unitful.jl, and we've provided additional astronomical units in unitful.jl. So those are kind of the fundamental packages that are out there. In terms of spectroscopy, there's spectralfitting.jl, which is being developed. This is primarily for X-ray spectra, but it's 3 times faster than XSPECT. And its long-term goal is to be multi-wavelength. Basically, the idea is that you only need one package to do spectral fitting. And We're also working on radix.jl. This is a synthetic spectra for basically creating synthetic spectra for X-ray photoionization. And to be honest, it's basically a Julia version of X-star. And we believe that by converting it to Julia, we can make it possibly 10 times faster than X-star. Core.jl is for stellar atmospheres, and that's being worked on. So there's some packages out there for doing spectroscopy. There's stuff for time series. There's dsp.jl. This is out of the general Julia package list. There's LOM-SCARGL for the Schuster periodogram. There's timeseries.jl, which is a toolkit. And there's bretthorst.jl, which also does periodogram. The difference, LOM-SCARGL is a frequentist derivation of the Schuster periodogram, and Bretthorst is a pure Bayesian derivation of the Schuster periodogram. The Bretthorst includes a function to do chirp analysis. In essence, you do the frequency in its first derivative, and then there's also one for the jerk, which is the frequency, its first and second derivatives. There's also a program out there to do twin frequencies. If you have two frequencies that are really close together, interestingly enough, you can actually separate them, and which you don't find. Those are not available in the LOM-SCARGL package. So there's some additional functionality out there for that type of data time series analysis. We've got some people developing photometry. We've got a CCD reduction.jl, photometry.jl for aperture photometry. There's a person working on photometric filters, basically providing a reference package for common photometric filters. There's PSF models, which will provide analytic point spread functions. And for actually looking at images, there's SAO DS9 provides an interface to the DS9 package. For radio interferometry, there's Comrade.jl, which is a composable modeling of radio emission. You'll hear that talk next by Paul Tiede. Somebody has written a wrapper for the DiffMap program, and we're beginning to work on Oris.jl, which is a package to do basically astronomical utilities for radio interferometry and simulation. The idea is to rewrite and have a pure Julia package for calibrating and analyzing radio data. We believe that the current software is not performant enough, and so we're looking to write something that's really fast, and so that you can actually analyze your data very quickly. Just to be honest, the cost of software that's out there takes hours to calibrate data. We believe we can do it within 10 or 15 minutes, just by better technology and a better language, new technology. There's stuff for exoplanets. There's the program called OctoFitter for exoplanet and binary star parameter estimation. The image you see on the left is basically an example of what it can do. It's a very complete package, and it's kind of a state-of-the-art app for doing exoplanet type searches. And you can see the graphics are very nice. So who uses Julia? There's Julia HCI for high contrast imaging. That's another different collaboration. There's Julia Space. There's a group to do astrodynamics and satellite mission planning. They've moved to Julia, or feel that Julia is necessary because of the performance it provides. EHT Julia for VLBI imaging of black holes, basically the next talk by Paul Tiede. There's cosmological emulators that emulate cosmological observables, and there's one not directly related to astronomy. There's CLIMA, the Climate Modeling Alliance, out of Caltech, JPL, and MIT. The CLIMA Alliance is doing a lot of advanced work in terms of developing Julia software and modeling for that. And there are various packages that have been derived from the CLIMA project. So I should say right now that our goal is to write a lot of pure, basically convert everything we have or code to pure Julia code, which is preferable to wrapping it in C. And the reason is performance is a primary reason. And one of the benefits that Julia has function broadcasting. You know, in Python, you're used to array broadcasting where you can use, do element by element, operations on an array. Julia allows this to be extended to functions. So if I write a function called func and it accepts a scalar argument, I can write it as func dot and give it an array, func dot period, and provide it an array, and it will broadcast that function over the entire array. You can also provide GPUs arrays and have that function run on the GPU directly. Okay, you don't have to write it in C or C++. So that's the primary reason for converting stuff to pure Julia, is the benefits of getting higher performance, particularly parallel programming. But wait, there's more. As I said before, Julia, outside of astronomy, has a huge and very productive, work that's going on. There's measurements.jl, which does uncertainties and propagation. There's Uniful, which does physical units. There's Jump, which is a modeling language for mathematical optimization, very sophisticated. There's symbolic, so you can actually do symbolic manipulation in Julia. I use that all the time. It's really nice, and it's 10 times faster than SymPy. There's plots.jl, which is a visualization interface, and there's an example of a plot that you can see on the right-hand side. And more, there's a visualization package called Mackie. This is actually the preferred one, and it's much more sophisticated than plots.jl. And so there's an example here, which doesn't seem to render very well, but you can see what the simulation looks like. Another aspect that Julia has is allows you to do GPU programming directly. There's a CUDA.jl package for the NVIDIA GPU. There's AMD GPU for AMD's, one API for Intel, and there's Metal.jl for Apple M series. So within just a few lines of code, you can take your Julia code and run it on the GPU if that's what you want to do for better performance. And these packages allow you to do that. This one really nice package is SciML for scientific machine learning. This is part of the CLIMA project in some sense, or at least the CLIMA, they work together with the CLIMA project. And this is designed to do physics-informed model discovery. And the idea here is that when you're doing machine learning and you're doing, various synthetic type models or so on, you don't want to just rely on the data. You want to be able to include physics into those equations, and SciML allows you to do that. So in essence, you're only using machine learning to cover those parts which you don't know well about and which you can't model accurately with the physics at the time. It provides advanced equation solvers for ODEs, SDEs, DDEs, and everything like that. Very sophisticated. And as I said, it's partly being supported or motivated by the CLIMA project, where you see examples of some climate simulations there on the right. So JuliaAstro, the website is what you might expect, JuliaAstro.org. The repository is on GitHub, that's JuliaAstro. There's an email list if you have questions, that's astro@julialang.org. We have a Slack channel called the Astronomy Slack channel. We have meetings on the fourth Wednesdays of each month. There's Zoom meetings, and once a year, there's JuliaCon, where we get together and discuss Julia and show what has progressed and what we've done in the past year. So that's pretty much about JuliaAstro. It's kind of a whirlwind tour. If there are any questions, I can take questions at this time.
Great. Thank you, Paul. We have fun reactions now. Some people have posted some questions in the chat, and maybe we'll take one, then we'll hear from the other Paul, and then we'll have a more general discussion afterwards. Oops, I didn't undo my video. First up from Sumner, and this one's a good one for you. What's it like to convert from Fortran to Julia?
That is a good question. So it really depends on how modular your Fortran code is. If your code is very modular, then it can be fairly easy. If you've got spaghetti code, old code, which is spaghetti, then it's going to be a lot more difficult. I mean, but it's interestingly enough, I mean, XStar is a Fortran code, that we're converting in basically the radix code. You know, the one thing is old Fortran code tends to use lots of for loops in it. Julia doesn't require that, right? Because it has arrays, it does array broadcasting. So that cuts down maybe, fifth the number of lines. So actually it can be fairly easy. And you can make it very concise. You can probably cut the number of lines of code down by a factor of 10 or more, and with better performance, because you can use the parallel applications and threaded applications that Julia provides.
Is there a Fortran bridge for Julia, like F to Pi, that could help along the way, or no?
Well, you can always, wrap the Fortran code. You can always use ccall, which also works with Fortran code, and just wrap those functions. Yeah.
Okay.
So, Julia, there is ccall for C and Fortran code. There's Python call to call Python. There's Julia call, which is to call Julia from Python. So,
right.
There's that interoperability is there.
Okay, great. I'll turn it back to Amrita for our next speaker.
Thank you. Our next speaker is Paul Tiede, who is a research associate with the Black Hole Initiative at Harvard and Smithsonian. Paul is a co-developer of numerous software packages that are used by the Event Horizon Telescope collaboration. And today he'll tell us more about Comrade.
Right, yeah, thank you. Okay, let me share my screen. Great. And can people see my screen and hear me?
Yeah.
Perfect.
No,
All
wait,
right.
one sec. I can hear you, but the screen just disappeared for me. Does anyone else have the similar issue?
Is it
Okay,
better now?
Yeah, but not in the presentation mode. Okay, now it's in the presentation mode. Okay.
Okay.
Yeah.
Great. Okay, great. Yeah, so I'm gonna talk about Comrade, and we should kind of view it as it's a bit of a case study of using Julia for radio interferometry and kind of black hole imaging and black hole analysis. Just quickly, a few things about me, just to paint my perspective, or you can see where my biases are going to be. I'm a research fellow at the Black Hole Initiative. I'm also an AWS Impact Computing Fellow. I am a quote unquote radio astronomer. I say that quote unquote because my training was never in radio astronomy. My background is in mathematical physics and really applied math. And in the last, I guess 8 years now, I've been a radio astronomer in some sense. Previously to my experience in Julia, I was primarily a C++ and Python developer. I helped write a 100,000 plus line C++ code base for the EHT a few years ago that we used throughout the first analyses. But I started using Julia in 2020. The lesson here is don't leave your PhD student alone for a few weeks. I was a I was a bored PhD student, so I rewrote a giant C++ code base in Julia in a couple of weeks. And then given that, I was like, oh, I'm just going to redo everything in Julia. So I did that for a couple of years as well, because the C++ code was becoming the bane of my existence. It was too difficult to develop in. Partially that's my fault because I helped develop it. But then also, hilariously enough, it was a little too slow, especially from a development standpoint and even from a performance standpoint. And I'll get into some of the reasons why. So my area of expertise is very long baseline interferometry. This is where you connect a bunch of telescopes effectively through computation to form a giant telescope that can be as big as the separation between the telescopes, like the physical geographic separation. So using stuff like this, you can turn the entire planet into a telescope. One of the really fun things about VLBI is I think it's fundamentally computation everywhere. There are dishes everywhere, but the first thing we do is we digitize the signal, put it onto hard disks, and then ship them to some central location. At this stage, the data is typically 1 to 10 petabytes. We then run them through specialized supercomputers that are called correlators. There's one in Bonn, Germany, and there's another one in Western Massachusetts, or MIT Haystack. At this point, this is kind of where you actually form the telescope. You cross-correlate these digitized signals and measure effectively interference patterns between these telescopes. At this stage, you're down to about 10 to 100 terabytes, just because there's some pretty substantial averaging that happens. But at this point, the data that you get out is completely noise. It's corrupted by crazy instrumental things, or I could give an entire talk about the kind of weird things we have to deal with. And so then there's this additional step that's called calibration, or if you're a radio astronomer, it's sometimes called fringe fitting, where you effectively find the impact of the instrument and the atmosphere, remove it so that you can effectively coherently average the data together. And this is the major step that pulls us from 100 some terabytes of this big data regime into something that's pretty small, where you're talking about 1 to 10 megabytes, or maybe a few hundred megabytes, or maybe a few gigabytes of data. But this calibration step is really where we can effectively remove most of the amount of data. There is one final step, though. The EHT and all VLBI interferometers don't actually measure an image. They measure the Fourier transform of the image. So there's this final little computation step where you have to go from this very sparse sampling of information in the Fourier domain and infer what the actual on-sky image is. This is called image reconstruction, or VLBI imaging more generally. And this is where we get our final result, and you're able to take a picture of a black hole. So kind of as a case study of this whole computational pipeline, and a fun little example that I think had a pretty big impact on the public, at least, was the Event Horizon Telescope. This produced the first ever image of a black hole on horizon scales, resolving this, what we call the shadow, in 2019. A couple years later, we kind of added polarization, so we were able to measure the polarization structure of the image and use it to try to infer what the magnetic field geometry around a black hole is. And then in 2022, we produced the first ever image of the black hole at the center of our galaxy, Sagittarius A star. This was really complicated because it breaks most assumptions in radio interferometry, so it took us a while. And actually, this paper used this Comrade and Julia ecosystem in, I think 4 out of the 6 papers. It was everywhere. So why did I pick EHT to kind of do this, or why is this kind of an interesting case study? It's a very interesting array. It breaks most assumptions from traditional radio interferometry. One is, I mentioned previously, VLBI measures the Fourier transform, or radio interferometry measures the Fourier transform of the image. EHT coverage is hilariously sparse. So people are familiar with ALMA. What ALMA natively produces is coverage that looks like this. This is for HL Tau, a protoplanetary disk. More standard arrays, like the VLBA, is part of which the Mojave program uses, is quite a bit more filled in. It's quite a few more arrays. You can get a pretty good sampling of the UV domain, although nothing like ALMA. M87 is sparse. There's about effectively 6 unique geographic locations, and something like eight stations in total that observe this source right here. So there's massive gaps. this makes imaging extremely hard. This also makes calibration really, really hard because you have a really hard time figuring these things out. So it pushes you into kind of a new regime for software. The other thing is that the EHT was never built or designed as a global instrument to work together. So it's a kind of effectively a ragtag group of very, very nice radio dishes, but none of them were built together. So everyone is its own unique animal that you need to figure out and characterize, and effectively every year. One of the fun things about it for the radio people here is it's actually an example of a mixed polarization interferometer. So that means that not all dishes measure the same components of the E&M field's polarization. So ALMA actually measures the two linear components of the polarization, and the rest of the array measures circular. This is unique. This was, for a long time, EHT was one of the only major instruments that had this, and this opened up a whole bunch of issues that we had to deal with. So circa 2019, the two EHT tools we used were written in, I would say, Python and C++. I helped develop the C++ code, so warning, bias. So they were really focused on two separate things. This EHT imaging code was kind of a maximum likelihood thing. It was really developed for, I think, kind of interactive desktop use where people wanted to quickly kind of poke around at data, figure out what was going on, and a much more interactive development. This C++ code was Bayesian, and it really focused on providing uncertainty quantification, and it was developed for distributed computing MPI HPC systems and required, as all C++ code does, to actually be useful for most people, a Python post-processing interface. So we actually effectively had two whole packages to actually use this package, which caused maintenance nightmares. I'll say at this point, both packages lacked autodiff functionality. This was happening in 2019. Autodiff was still kind of new, and the packages that did exist, like PyMC, didn't really support the kind of things that were needed from EHT imaging. So what they did was they used handwritten gradients everywhere. This really limited the space of models they considered, because there's only so many gradients you want to derive over and over and over again. And so this kind of just slowed everything down. There was some work to port this package to JAX a few years ago. It stalled due to difficulties in JAX. Some of the limitations are quote unquote sharp bits that they list. A lot of the things we do and a lot of the things that were written with this package require some amount of dynamic control graphs and a bunch of things that JAX just has a really hard time handling. And I think for some of the setups that we have, there wasn't a big performance improvement over NumPy. So it just effectively stalled. For Themis, it was a C++ code base. Getting stuff to work with autodiff there was a bit of a nightmare. So we cheated and just used gradients with finite difference in MPI to distribute over giant infrastructures using like thousands and thousands of cores. The end result of this, though, was that I think we were very successful, but it took a ton of compute. EHT imaging, with its Python-based thing, took about a week with 100 cores to produce this image. Themis took about a week with 1,000 cores. It also fit a very restricted type of model. And in a result, this kind of performance that we had is a bit of a massive problem. I need to update this. This is now 3 years, but the EHT has only published 3 years of observations, 2017, 2018, and 2021. But we have data from multiple epochs, 2017, 18, 21, 22, 23, 24, 25 as well. And we're going to be doing a movie campaign in 2026 where we observe M87 weekly. The EHT is continuously getting better. We're adding more dishes. So this makes the performance more problematic. And we're going to really quickly run into a regime where these kind of performance characteristics are just not acceptable for us to keep up with the amount of data. So this kind of motivated a new set of imaging, or a new set of codes for kind of imaging black holes. The three things that I wanted to keep in mind when we were doing this was, one, performance. This kind of VLBI imaging typically has thousands to billions of parameters. If you want to do Bayesian inference or even some sort of optimization scheme, you need thousands to millions of evaluations of a likelihood and its gradient. And I will say our data can exceed petabytes for a night. We're pretty concerned about the NGVLA, whose recording rate is 1 terabyte a second, and we're going to have to deal with this in the next decade. So having performant code is critical so that we can actually analyze the data that these next generation instruments are going to produce. The other thing is that this black hole imaging, at least, and I would say VLBI in general, we want really flexible and composable models. This is because we really don't know what we're looking at. We barely understand a lot of the physics that's going on. And so that means that we have an incredibly wide class of models that we like to consider, from really simple things like rings on the sky that were used in the original EHT papers, to ray traced and radiative transfer accretion models that we want to be able to propagate through and do direct inference on, to just these kind of more agnostic imaging methods. What this means is that we have nonlinear models everywhere. We need to support all kinds of things that are classic in HPC scientific computing. This means mutation, control flow, dynamic control graphs, etc. And we need to be able to automatically differentiate through it all, hopefully simply, so that an astronomer doesn't have to worry about all of these technical details. The other thing is that, astronomers, we are not computer scientists. I don't think we should try to be computer scientists. That is not a good use of the skills that we've all been trained for. And one of the big things that's really beneficial for our kind of analysis is interactivity, ease of use. This is where things like static languages like C++ have proven to us, at least in the EHT, are not very helpful. It's very nice to be able to have a Jupyter notebook open, or some other notebook environment, or effective interactive terminal or REPL to kind of play with things. It really aids development speed to be able to write a little bit of code, see what's going on, and tweak things as you're going, or do some little data analysis and effectively have immediate feedback. That's much more complicated if you're directly interfacing with something like a compiled language and you have to recompile when you want to change something in the code. So to come up with this, I developed Comrade. It's a mouthful. It's a horrible acronym, but it was kind of, I was joking around when I was doing it in the middle of COVID, so maybe I was in a fugue state. The acronym stands for Composable Modeling of Radio Emission, and it's built on 3 pillars. One is Julia. Paul just gave a great overview of the benefits of Julia, but I'll just hammer it home again a little bit. It's a high-performance scientific programming language. It has similar speed as C, but it is pretty simple to use. I have pretty good examples of this at this point. I've had several students who have before hadn't had any prior experience with Julia, and they've contributed massively to the code and have started their own really fantastic kind of research project. So if students can use it, it's simple enough to use for me, so I'm happy about that. It also supports, it's an actual programming language. JAX is not, so it supports things like loops. Loops are fast. It has control flow. It has GPU support. It has MPI support. It's a language. It's an actual programming language. The other thing is that we've made massive use of is something called Enzyme. Enzyme is a compiler level automatic differentiation suite. It basically computes gradients based off of something called LLVM or MLIR based kind of like lower level language called intermediate representation, or IR. The benefit of this is it has cross language support. So one of the party tricks is that if you can compile your code with an LLVM based compiler, we can technically auto diff through it through Julia, or any language for that matter. So it provides the ability to kind of reuse existing software already and to be able to compute gradients for it. It also, and this was critical for us, has much broader support of automatic differentiation for specific things. So for instance, it can AD through for loops, and those are ridiculously fast. It supports mutation. I can mutate arrays all I want, and it handles that fine. It handles control flow. It also will natively AD through GPU kernels for you and compute the GPU kernels and do it in an efficient way. Similarly for MPI, there's a few papers that talk about this, but this was effectively a game changer for us. Finally, Comrade's Bayesian. I'm a Bayesian person, so I need to compute uncertainty estimates for everything. So we do that for everything. I won't go into that too much, but that's one of the quirks of or I would say benefits of the language. So in terms of benchmarks, what does this get you? So Just a reminder of this Python and C++ code base in Julia with Enzyme. We were able to turn this into about 30 minutes on a single core. So I'm able to do kind of publication level imaging in 30 minutes on my laptop, and we're able to scale to much bigger models. So it typically will fit thousands to millions of parameters, and it hasn't been a big deal for us yet. So this was a pretty big game changer for us, and as a result of this, it's about a 10-to-3 improvement in time and resources, and it's being used more and more, I think, within the EHT. And how did Julia do this? Well, Julia is fast, for loops, control flow, everything. An example micro benchmark of one of the really simple problems we have to solve. Python is typically an order of magnitude or 20 times slower. This is about 14 times. It is also, this was surprising to me because this was C++ code that I did spend some time trying to make fast. The same code in Comrade, I was able to get about a 2 times speed up over the C++ code. And that was kind of a big deal for us. So it's an example that Julia is and can be as fast as C++. I'm not saying, you might immediately do this, but it's very easy to make fast code in Julia. The autodiff system, again, so we typically will have gradient overheads that are about 2 to 3 times slower than the forward call, or from just evaluating the likelihood. That's very good. For Python, the overhead is effectively much worse. And so we're about 20 times faster in computing a gradient. And for Themis C++, because we didn't have an autodiff functionality, we had to do finite difference. So to get close to the Julia performance on a single core, we had to do 16 cores with MPI, and we were able to get it within spitting distance, about 30% slower. And I'll say in general, the Julia autodiff system is maturing pretty aggressively at this point. There's Enzyme, which is my favorite, but there's also others like Mooncake, which is a native Julia implementation that's not quite as fast as Enzyme typically, but typically within a factor of 2. There's also a really flexible forward diff package that tends to be very simple to use. There's some sharp bits with Enzyme. Forward diff is like, you just give it your Julia function, and if you've written generic Julia code, you'll get gradients for free. This also really helped scaling with us. So because we wrote this within Julia, I got way better scaling than in C++, where I had to hand roll a bunch of things. I'm no computer scientist, so computer scientists are better than I am at implementing things. And what this really comes down to is that the Julia language itself is flexible and composable. Within Comrade, because of Julia's package management, I was able to reuse several existing tools and include them in the package. I'll also say, compared to Python, Julia doesn't really want you to do big monolithic packages. I actually view this as a benefit because it makes it easier for things to become composable. And then compared to something like C++, where if you're trying to build in or get external packages, setting up the whole compiler and build system is a nightmare. I, for instance, spent weeks or about a month or a few months trying to, and succeeding, but interfacing this C++ Themis package with a very popular probabilistic programming language called Stan. That was a nightmare to get going, and I would not recommend people do that. In Julia, it's as simple as package add Turing or package add your favorite MCMC package. And I think the net of this, just as a kind of quantitative example, for similar amounts of functionality, the Themis lines of code was about 30,000, and for Julia, or it was a little over 30,000, and for Julia, it was a little under 3,000. So an order of magnitude improvement in the amount of time. Anecdotally, for Themis, we had a team of about 8 people building this thing in C++. In Comrade, the team was me, and it was me sitting in my room during COVID and just kind of building a pretty quick little package. So at least personally, I had a massive improvement in my productivity. So this has pushed EHT science forward. It was used extensively, this Comrade package, in the most recent EHT result that showed the variability of M87 across 3 observing epochs, including the polarization. I was the co-lead of this, but Comrade was really a big reason that we were able to push these images out, and I think a big reason why we were as confident with the results as we were. It also works for other VLBI arrays. Here's an example of PKS 1424. This was in the press recently. It was called the Eye of Sauron. It's a blazar that's effectively, we're looking directly down the barrel of the jet. Here's an example of a single epoch clean reconstruction. They really struggle to measure polarization in this. And they really required multiple epochs stacking to dig out the polarization signal. Due to some of the algorithmic choices and scalability of Comrade, we're able to reconstruct a polarized image structure in a single epoch and produce something that looks similar from the multi-epoch stacking. So this is kind of a big deal, at least for us from a science perspective. We can also scale to very big field of view images. Here are some soon to be published results for a couple of sources. This is M87 at 15 gigahertz. You can see things like limb brightening in the jet. You also see this little counter jet, and because we're Bayesian, I can produce uncertainty maps, and which means I can assess the significance of features. So in a single epoch, we're able to effectively get an over 4 sigma detection of the counter jet in M87, which has been talked about a lot. We also get pretty improved super resolution, so we can start measuring these limb brightened features and things and really improve dynamic range, so you can see big ploofy jets kind of bending around sources. This is fun for us. I won't go into too much about it, but pretty pictures. I like pretty pictures. That's all I do. Where we're going, I think our big thing is, I mentioned this calibration. I want to use a similar approach to calibration. CASA you have to have specialized hardware or specialized systems for CASA to work for us. We effectively need, every single node has to have multiple terabytes of RAM because we're so memory limited with CASA, because it does very silly things when it's loading the data. And so you need these very unique clusters or effectively specialized machines. And then it's super slow. It takes a month for us to analyze the EHT data and fringe fit it. You can imagine if you get it wrong, that means you have to wait a month again. I think Paul mentioned this, but we should be able to turn this into days, just using a more modern language and taking advantage of GPUs. So to support this, I have been inspired by all this work. And so we're going to be building on a bunch of compiler ecosystem stuff with reactant. It's effectively a thing that will read your Julia code, convert it to something called MLIR, and we'll get automatic support for GPUs, CPUs, and AI chips, because those are the big things these days, Trainium, Google TPUs, and so forth. And then we'll be able to AD through everything with Enzyme. And for people who have handwritten their GPU kernels, we can actually, this is a fun party trick developed by Billy Moses, is we can read your C++ or your CUDA code, raise it to MLIR, and immediately port it to GPUs and accelerators. But I am done.
Yeah, thank you.
Yeah. Okay, yeah, that's it. I am sorry for going a little over.
All right. Well, thank you, both of you, for nice talks. We have some discussion in the chat, which some of you have been going through. There was a mention of Pluto.jl reactive notebook as an alternative to Jupyter to get around that whole thing of changing something downstream and then getting all confused, which we've all gone through. I think there's similar things in Python for that as well. There's a question about Bayesian MCMC packages. Do one of you want to talk a little bit about Julia MCMC packages, if you have any experience?
Paul, do you?
Yeah, I can take this. So I'm a big MCMC user. I think Julia's MCMC infrastructure is actually very strong. There are MCMC kind of things if you want to do the infine invariant. I have a whole thing. We talk about my issues with that package, but there's other packages in Julia that are very good for MCMC. I mentioned one is called Pigeons. It's a non-reversible parallel tempering. I've literally never seen a problem for dimensions under about 100 that it can't sample well. It's HPC ready. It runs on clusters. It's very, very nice. Developed by statisticians. I think the Julia MCMC package is very good. And I think Nico was saying, yeah, in cosmology, there's tons of really good packages for this. So you should utilize them. So I think Julia's MCMC is actually pretty good. It's one of its stronger suites.
Great. There's also Brendan pointed out Jack as a sort of something in spirit to Cocos. I don't know if any of you have any experience in that. Cocos is getting very big in Astro for performance portability. But maybe one of you can say something about most of what you did was, working on Astro data, but in HPC and Astro, you have to run across thousands of nodes, tens of thousands of GPUs. Is there a Julia solution for that?
There is MPI. You can always run MPI. There's
Right.
also things like Dagger, which is like a Dask type thing where you can form a directed acyclic graph and it will automatically schedule it on thousands of nodes that have been useful. There's also built in Julia things like distributed. This reactant thing I was talking about as well, you can think of it like Cocos in a sense, where if you specify how you want to shard the data, it will automatically split it on all CPUs for you. So for instance, Billy Moses ran this on, I think, 10,000 Google TPU chips as part of Google Cloud Computing, just utilizing the same code, just said, all right, split the data along this axis, and then it split it and ran the computation. So it's being developed, I will say.
Okay.
I'd like to add at the last JuliaCon that this was discussed, and one of the motivations for Dagger, and I'm sure there's others out there, is that you should be able to just give it a problem, tell it what resources you have in terms of GPUs, nodes, and all that type of stuff, and it figures out how to distribute that and run it for you. Okay, so in essence, you don't have to have understanding of the computing. You just have to understand your resources and go from there. How soon that will occur, well, we don't know, another few years off, but there is the effort to make it very distributed and portable. The other little thing that's even for, laptop users is that Julia has is it's very easy to do multi-threading, particularly if you have a for loop where every iteration is independent. You can just, in front of that for statement, you can just say @threaded, and it will thread that entire loop for you. So if you've got 16 threads, immediately that for loop now runs on 16 threads. It's just that simple. And, for someone like me who doesn't do a lot of parallel processing, I find that really nice. For Paul, I'm sure he has other things that he does, but there is that little feature there that's built into the language.
And what would you suggest for introductory resources? One of the issues I've always had with Julia is there's no official tutorial. You go to their website and there's too many tutorials, which means you don't know which one to use. And Python has a nice official tutorial. And I always wish Julia would do that.
Well, a good start would be to sign up for my workshop at the SS meeting in January, my 2-day workshop on the introduction to Julia. I would appreciate that. That's one reason I have them there is to introduce people to the language. And we are working on it. It really comes back to the issue that we are resource limited. And there's, we're still research scientists. And so,
who's the we here? The Julia or JuliaAstro?
JuliaAstro.
Right. I'm talking specifically about the bigger Julia, not just JuliaAstro.
Yeah, I haven't really looked into that. I develop my own, learning materials, and
right.
And so basically, from my workshop, those tutorials will basically go out onto the JuliaAstro website at some point.
Okay.
We're revamping them to hopefully make them a little bit easier for people to get into, and to get to ramp up quickly with Julia.
I think I did most of the major discussions. If anyone has a last question, they want to raise their hand or just unmute.
I will say there is actually a nice kind of Julia workflow thing if you want to go through that was developed recently. I'll add a link to it in the chat. It's called Mojuwo. It's a kind of a mouthful, but it's pretty good. It gives you an idea of how to run Julia.
Yeah, that'd be great.
I just added it to the chat, but yeah.
All right.
There's also the Think Like a Programmer Julia
Right.
software, which
Al,
I don't
is
know how
that
good they are,
Allegheny
but
stuff or no? Or maybe not. All right. Well, thank you both. And thank you everyone for attending. We will, well, everyone hopefully enjoy their holidays. Maybe Amrita, you have some last words.
Just thank you for supporting us through 2025 and joining our sessions and giving your inputs and participating. We look forward to a productive 2026.
Wonderful. Thank you. Trying to stop recording.